Alright, so in this video I'll attempt to explain how the RF section of a software defined radio actually works. And then I'll move on to some real world examples with open sourced SDR platforms like HackRF1 and the Lime SDR Mini. So this in front of you, which you're seeing, this block diagram is the basic system block diagram of a transmit and receive capable SDR. Now this can be a little intimidating to beginners because there are so many different components and they're interacting with one another, but once you start breaking them down, breaking the entire schematic down into smaller, more simpler building blocks, I can assure you that the entire process of dissecting the RF chain and understanding how it works becomes very simple. Now, before I move on with the video, I expect you to have a working understanding, working knowledge of what super heterodyne radios are and what IQ signals are. Where did the G disappear? All right. Now, I'm not expecting you to be an expert on these topics, but at least how the block diagram of a superhet radio looks like, what is an intermediate frequency, what is a mixer, why do we need local oscillator signals, and all of these things. And on the other hand, why we need IQ signals and what are IQ signals. If you do not have an understanding of these topics, you can head over to the YouTube channel which goes by the name W2AEW. This is his ham radio call sign actually, but I have found his videos to be pretty informative, very concise and very helpful for RF stuff. Alright, so now that's out of the door, we can actually dive into the subject. Now in this schematic we are going to move from right to left in the bottom section, go up to the antenna, and then move from left to right in the top section. We are going to do that because we want to follow the signal path. Now in the bottom we have high-speed DACs, and on the top we have high-speed ADCs. Now DACs are used for signal transmission, so this is the transmit path, and ADCs are used for signal reception because they're converting analog domain to digital domain, so that is used for signal reception. This is the signal receiving path. Okay, so you can also see that we have FPGA. Now the main requirement of the FPGA is that it can handle IQ baseband digital signals. It can receive them and operate on them, or it can generate them for transmitting through a DAC. And also there are other requirements of an FPGA like encryption and encoding. Anyway, there are similar requirements for the FPGA. So in modern SDRs you would often find FPGAs or other kinds of CPLDs. Alright, so first we have the high-speed DAC. Now the speed of this high-speed DAC is determined by the baseband bandwidth of the IQ baseband signal. If let's say we are trying to achieve a bandwidth of 5 megahertz, then we can do with a 10 megasample per second DAC, but that is the extreme. So that is why a a speed of around at least 30 to 50 MSPS is required for generating 5 megahertz bandwidth signals. Now these high-speed DACs are generally in the range of 15 megasamples per second to it can be 300, it can be 500. It entirely depends upon your baseband bandwidth and your RF parameters. But let's consider this is a safe zone to play with. All right, so the DAC's responsibility is to convert digital IQ baseband signal to analog IQ baseband signal. Now mind you that these up to this modulator, it is baseband. Baseband means that it is only the message signal. If it is a voice, then it will be up to like 5 kilohertz or like whatever the voice bandwidth is required for that application, it will be that. It won't be in megahertz. So we can do some kind of signal conditioning with low pass filters, band pass filters on this baseband signal, and after that we can modulate the IQ signal, and after modulation it performs signal translation or frequency translation into intermediate frequency, and this intermediate frequency signal would be IQ modulated signal. So on this intermediate frequency signal we can apply again some kind of signal conditioning like amplifiers or band pass filters or low pass filters, and then we have the stage of the mixer. Now the mixer is required because generally in SDR applications we are aiming at a wide range of RF spectrum, because on one hand we want to, let's say, receive or transmit ham radio signals, and on the other hand we also want to receive or transmit 5G signal data. So for that application we might need a radio which can go from let's say 30 megahertz to 4 gigahertz. So that is why the mixer is used. In the mixer we are feeding a local oscillator signal and the IF signal, and we are getting RF as output, just like a super heterodyne radio. So the RF output would be either the additive sum of LO and IF signals or the difference component of LO and IF, depending on whichever is the larger in frequency, LO or IF. Now by tuning the LO frequency, we can have a constant IF and achieve a range of RF signals. Now once we get the modulated RF signal, we can do further signal conditioning and then feed it to, in this case it is an RF switch. Now the RF switch can either connect the single antenna, which we have here. We can also by the way use two antennas on the receive and transmit section and completely eliminate the need for this RF switch. But in that case we have two different antennas that might not meet the requirements of your radio. So in this case they have a half duplex system where there is one single antenna and it is duplexed between receiving and transmitting at one time. So let's say we are switching it to transmit. So the antenna would be coupled, would be connected to the transmit channel, and we can feed the RF modulated signal to the antenna, and then it will radiate it to the outside world into free space. All right, so that is how the transmit chain is working generally. Now the receive section is also working in a very similar manner. Let's say we are receiving a wide range of signals, almost white noise, into the antenna. We are shorting it to the RX chain, the receive chain, and then we have this entire RX chain which we're going to decode right now. So the only thing I find missing in this block diagram, by the way, this block diagram is taken from Maxim Integrated's SDR product selection guide or component selection guide. You can check it up on the web, or I might even put a link down there in the comments. Anyway, the component which I see missing is a very key element, which is a band pass filter. So through this antenna, you're receiving almost white noise. You're receiving a wide range of RF spectrum. You have to select which frequency you want to receive. So that is where the band pass filter comes in. Once you selected that frequency, you can detect the power of the received signal. That is why there is a power detector. You might not need a power detector. This is entirely dependent on your use case. And LNA is almost always required, because otherwise the received signal strength is so low that you can't even demodulate it or do anything with it. So LNA is almost always required, and then we go to the mixer stage. Up till the mixer, we have RF modulated signal. In the mixer, we are feeding again the LO, and the LO frequency is set such that we hit the required intermediate frequency. Now, the requirement of hitting a particular intermediate frequency is because the IQ demodulator and the IQ modulator generally works on a very narrow band. I mean, I shouldn't call it narrow band, but a much narrower band of signals than what we require in the SDR. There are some IQ demods, there are some IQ modulators which are working in a very wide band signal range, and in those cases we can eliminate a lot of the front end components like the mixers and all. But generally it is a good practice to know or be aware of this entire chain, because there might be an IQ demodulator which is very cost effective and you have to use it for the design, but it is only operating from 2.3 gigahertz to 2.5 gigahertz, but you have to hit a frequency range of 30 megahertz to 4 gigahertz. So in that case, you absolutely need a constant intermediate frequency. So once we do some signal conditioning on the intermediate frequency, we can perform demodulation, and this is IQ demodulation, quadrature demodulation. So we get I signal and the Q signal. Again, some kind of signal conditioning, low pass filters in this case, and then ADC buffers. Buffers are used because we don't want to load the signal because we are feeding it into the ADC. So sometimes ADCs include ADC buffers inside the IC itself, but over here it is just shown as a different block because that is a required block before feeding it into the ADC. Now into the ADC we are feeding I and Q baseband signals in the analog domain. Now up to IQ demodulator from the mixer we have IF. After IQ demodulation, very similar to the transmit section, we have baseband. Now after the ADC receives IQ baseband signal, it converts it into a digital IQ baseband signal and feeds it into FPGA. Now the feeding pattern or the feeding protocol can be different. It can be parallel interface, it can be LVDS, it can be JESD204B, but there are different kinds of interfaces to interface an ADC or a DSC with an FPGA. But anyway, it is feeding the digital data into the FPGA, and then the FPGA is getting digital IQ baseband data with which it can do further encoding, decoding, and further processing. Now, this is an overview of how the entire system is working. So just to reiterate the entire signal chain, we have let's make it bigger. We have data converters here, which are responsible for converting digital domain baseband signals to analog and vice versa. We have IQ modulators and demodulators here, which are converting baseband to intermediate frequency or intermediate frequency to baseband. Then we have the mixer stage, which is a very key component in the SDR, because we want to hit or we want to achieve a very wide range of frequency, which in most cases IQ demods and IQ mods cannot do. That is why we are using the mixer. The mixer is getting a LO feed signal, which is a variable signal which is being generated by the PLL. PLL is over here, if you can't see that. Yeah, that is the PLL. And oops. After the mixer, we are getting RF modulated signal, which we can transmit, or while receiving, we are receiving the RF modulated signal, which is being fed into the mixer. There are other signal conditioning components over here, and the antenna over here. So that is the complete overview of how an SDR is working right now. Let's go to the HackRF block diagram. Now this is the hardware of HackRF. If you look at the PCB, you would see a microcontroller, microprocessor over here, FPGA over here, and the RF section is over here. And this is the half duplex RX output input. So in the block diagram also, you can see a very similar structure, which I explained over here in this block diagram. So we have the DACs and ADCs in one single component, which is the MAX 5864. It's a very convenient structure. It's a very convenient package for SDRs, because we have IQ DACs and IQ ADCs in one single IC. This is the CPLD or FPGA, which is handling the IQ digital domain signals, digital domain baseband signals, and then we are having the DACs and ADCs to convert it into analog domain, and then we are having this transceiver, which is converting that analog domain baseband signal into analog domain IF signal, or vice versa, converting from analog domain modulated IF signal to baseband signal, because this has inbuilt IQ modulators and demodulators. You can see it in this stage. This is the IQ modulator, and this is the IQ demodulator. Alright, so after we get the IF over here, there are a series of switches, RF switches, which are determining the RF path. Now, since this is a half duplex system, the RF path has to be determined, because at one time it can only receive or transmit. That is why all of these switches are determining the RF path. And here we have a PLL with a mixer inbuilt into that IC, so that frequency translation is in one package IC. So this mixer is again responsible for converting IF to RF or RF to IF, given the LO signal from the PLL. And after the PLL mixer IC, we are having RF, oops, sorry about that. We are having RF signal over here. Now here we can do signal conditioning with high pass filters, low pass filters, LNAs, BAs. Bias T is placed over here, and then finally transmit it out of the antenna or receive it through the antenna. Now if you compare these two blocks, you would find like it is completely identical logically. So over here also we have ADCs, DSCs, modulators, mixers. Over here also we have ADCs, DSCs, modulators, demodulators, mixer, and then RF. Now we're going to look at a similar SDR, but over here the entire RF section is enclosed in one IC. This is the LMS 7002. We also have a LMS 6002. 6002 was before the 7002. And over here also, this is the IC block diagram. Inside the IC what the structure is. Over here also you can see that it is very similar to the standard SDR RF block diagram. So here we have ADCs. This actually has dual receive and dual transmit channels. So it has two dual ADCs and two dual DACs. Here is some signal conditioning stage, and over here we have the IQ demodulator, two IQ demodulators and two IQ modulators for receiving and transmitting, and then some more signal conditioning, filters and amplifiers, and more filters. And yeah, so you can see that it is very similar. The entire logical block is kept same throughout whatever kind of SDR it is, whether it is a on-chip SDR where all of the RF functionality is on one single IC, or whether it is a slightly more distributed SDR like the HackRF one. Also lastly, let's look at the LMS 6002. Over here also you'll find a very similar structure. So here we have the IQ DAC, IQ ADCs. LMS 6002 has single channel output, single channel input. So we have only one pair of DACs and one pair of ADCs. Signal conditioning, signal IQ modulator and IQ demodulator. Again, some signal conditioning, and then out into the analog world. So yeah, that was a brief overview of what or how SDRs are designed nowadays. Actually, nowadays there is another concept, another way of designing SDRs, which is called direct RF. So here we are using so many different analog components like mixers, IQ demod and modulators and all of these things. Those things can be replaced by direct RF components. Now direct RF basically means that you have a DAC, let's say, which is a very high speed DAC, much higher than the high speed DACs which are used over here. So these DACs would be in gigasample per second range, ranging from something like 2 to it can go into tens of GSPS, like 20 GSPS, and of course with more speed and more accuracy, I mean bit depth, the cost also increases. Now the HackRF one is a relatively medium to low cost SDR. If you have a low budget for your hardware, you can go with something like the HackRF. Now the entire RF chain of HackRF costs around 4,500 rupees, but one single LMS 7002 IC would set you back 9,000 rupees. So with more complexity, with more speed, the cost also increases. That is a key consideration when you're designing these systems. But once you have a DAC at this speed, let's say you have to generate a 500 megahertz modulated signal, and you have a DAC with 2 gigasample per second speed, which can easily generate a 500 megahertz signal without the need of any mixer, any IQ modulator. Actually, IQ modulation and everything is done digitally inside this component only, and it has one digital interface with a FPGA and just one RF output, or multiple RF outputs depending on the component. And similarly for ADCs also, same things apply. Yeah, so this is another different domain which you can explore, direct RF synthesis, but also the cost and everything increases. Complexity, PCB standards, and meeting impedance matching and high speed PCB ratings, all those things come into the picture. So yeah, I think that is a complete overview of what I was trying to convey. Yeah, all right, I hope you enjoyed the video. I hope it was informative. I hope it helped you in your journey into software defined radios, and I'll see you in the next video. Goodbye.